what I'll be talking for the most of the talk about is how we can get to utility scale quantum computing and how we can trap and control millions of qubits, how we can anticipate errors that we will see in scaled devices, even if they aren't large now. And third, how we can use our understanding of the device level, as well as our understanding of the application level to design the optimal architecture, and so that we're not doing too much work and still getting the fidelity and the speed that we need. So to set the scene and kind of so that we're all on the same page of what we need, I'd like to quickly talk about one potential application of quantum computing, which is quantum simulation. So one thing that we could do with a digital quantum computer is that we could encode the electronic dynamics and the electronic state of a molecule such as this, such as nitrogenase. If we could understand both the ground state of this molecule and also the dynamics of this molecule, we could hopefully use it and replace the Bosch process and make fertilizer faster and maybe solve world hunger. But if we wanted to do that, people have done estimates of what resources we would need. And if we want to do this in a fault-tolerant way so that we are sure of the results, we need potentially 100 million physical qubits and 100 terahertz, 100 teragates, right? And that, of course, these numbers depend on your exact implementation, but just to get like an idea of the order of magnitude. And this is for a classical computer, no problem. But for a quantum computer, this is much larger than we have now, where we have about maximum 100 qubits, and we can do kind of maximum 100 gates. And maybe to put this even more in perspective and to make this look even scarier, if you had to do this, these teraflops in succession, and maybe some of them you can do in parallel. So this is particularly pessimistic estimation. But if we have 100 microsecond gate time, and keep these numbers in mind for when I tell you how slow trapped ions are later, it would take 325 years. And that is not very useful. Even if you had a microsecond gate time, it would still take 3 years. And maybe this is okay if you couldn't even hope to do it on a classical computer, but it's still not great, sounding great for the utility of quantum computing. But we hope that as our devices get better, we can decrease this number. A lot of this overhead is due to fault tolerant, making sure everything is fault tolerant. And as we make our algorithms better, we can reduce the number of qubits and the gates that we need to encode. So we're working on both sides of this process or this problem. We're really working from the bottom up, but there's plenty of theorists out there working from the top down as well. But just to say that it maybe looks daunting. So today I'm going to talk about how we're hoping to pick away at these problems and help solve some of these hindrances towards utility scale quantum computing. First, I'll talk a little bit about the qubit that I use, which is singly ionized calcium-40 atoms. Then I'll talk about our work on kind of understanding the specifications that we will need to trap millions of qubits and be able to run gates at the speed that we need to. Then I'll talk about how we can measure those millions of qubits. And then finally, I'll talk a little bit about two errors that aren't really considered now, but they will become more and more prevalent as we scale up our systems. And I'd also like to say, this is a pretty small room. So if anybody has questions, this can be a discussion. So feel free to raise your hand and we can talk about things. If I don't get through all my slides, that's all right. Okay, so let's begin. Before I begin, I want, if you fall asleep after this slide, that's okay. I saw there's a lot of snacks outside. It's right after lunch. But this is the one thing that you should take away. Trapped ions are high quality qubits. So if I have a single trapped ion, it is more or less the best qubit that you can find. Or among the best qubits that you can find. We can do very high fidelity control with many, many nines. This is a single or two qubits. But if we want to increase the scale of these systems, it really becomes an engineering problem. So this is basically my talk summed up in one sentence. So our qubit, as I said, is calcium-40, singly ionized. We start with a gas of calcium-40, or we start with a chunk of calcium-40 or chunk of calcium that we heat up. And then we have a two-step ionization process where this is isotope dependent. So we can make sure that we're only ionizing calcium-40. So we use these two lasers to create to rip off one electron and create a 40 calcium plus. And then once we have that, we can trap this ion in electric fields. So if you remember from E&M, you can't create a fully trapping potential just with static electric fields. But if you use an RF potential, let's see if I can make this work. Maybe, yes. The RF potential, if it's moving faster than the movement of the ion, you can create this pseudo potential. And just like in that figure, your ion is trapped at that central location, trapped at what we call the RF null. And we do that in the general case by using a 4-rod trap where we have 2 electrodes be RF and 2 electrodes are ground. And so you create this pseudo potential, so this time average potential that traps the ion right at the center here. And then you'd have 2 electrodes in and out of the page, 2 DC electrodes to confine it in the 3rd dimension. What people more recently do is unfold that trap so that you have your 2 RF, 1 ground, then you say, okay, I have another ground plane up at infinity. And so you still create a trapping potential, maybe not quite as nice as this, and we'll quantify this later, but you still can trap an ion, you trap it around here. Okay, and what's nice about this is that you can create these electrodes through standard microfabrication processes. So this is a trap that we built at UW, where the purple are the RF electrodes, the yellow is the ground electrode, and the blue are different DC electrodes. So we could trap a few different chains of ions at these different locations. You could trap maybe 4 chains of ions. Whether you could use them all is a separate question, but you could trap a lot of ions. And this is just with standard silicon fabrication, and then we plate it with gold on top. And you can, people have made much more complicated traps than this, and that's kind of the standard way to trap lots of ions at the moment. Once we have them trapped, we can cool them to the Doppler. We can cool them quite a lot, but we can cool them to the Doppler limit through this dipole transition. So we have a dipole transition here at 397 nanometers. And this is, we can scatter a lot of photons, which means that our Doppler limit can be quite low. Yeah.
Before that your trap would be shallower basically when you do it on this chip thing. So how shallow does it get, and does your micromotion become problematic? I guess all of that is not a problem, but can you say a little bit about the comparison between the...
I will talk a lot about this in maybe 5 slides. So yeah. I will say just really briefly, depending on how you make them, but there's orders of magnitude different in the trap depths between these two. But you can get very high fidelity quantum computation in a surface trap. You just need more RF power to be able to create, a strong trap. Yeah, but I'll talk about that in detail in a second. Okay, great. So we have our ions trapped. How well we'll see in a second. We cool them. We can cool them to kind of tens of quanta using Doppler cooling by scattering photons off of this transition. We can cool it to near the ground state using sideband cooling, which I won't get into, just so for the experts in the room, we can get down to 0.1 quanta or below, which is nanokelvin temperatures. Then our qubit, we encode in calcium-40, we encode in this, we call it an optical qubit because this transition is optical. And this is a quadrupole transition. So if you remember your atomic physics, it's disallowed, as we learn in our first grad level quantum physics, but it is weakly allowed, but we have quite a long lifetime. We have a longer than second lifetime. So this becomes quite a good qubit. And we can run single qubit gates by exciting at 729 nanometers, and the phase can by controlling the phase and the amplitude, we can get anywhere we want around the Bloch sphere. And we run those gates in about a microsecond, and we can do them with 4 nines of fidelity, or about 10 to the minus 4 errors, so very high fidelity. We read out with the same transition that we cool. So we scatter photons off of this dipole transition, and we will only scatter photons if we're in the 0 state. And if we're in the 1 state, we won't scatter any photons. So we call this our bright state and our dark state. And if we look at the histogram of the photons that we get out, or if we're in the bright state or the dark state, we can see that we can get very strong separation. I mean, this is a particularly good graph from the company IonQ, but even in the lab, we can get such nice separation between our two states, really limited only by the lifetime of this state. So without trying too hard, we can read out for about 100 milliseconds, about 500 microseconds, so about, maybe about a millisecond, half a millisecond, and get pretty good fidelity, but we can also use fancier techniques to read out faster with even higher fidelity. The state of the art is maybe hundreds of microseconds or a millisecond with, again, 10 to the minus 4 errors. And then before I talk about entangling gates, we have to introduce some motional modes. So when I have one ion in a trap, our trap frequency, the secular frequency of our trapping potential is about 1 megahertz, that level, which means that, and this is a harmonic trap, so we get harmonic oscillator modes in all 3 directions with mode frequencies around 1 megahertz. And these modes, as I said, they can be cooled to near the ground state. And then if we have 2 ions, then we have 2 modes in each direction, the one where they move together and the one where they move apart. And if we have n ions, we have n modes in each direction, or 3 n modes in total. And these modes can be cooled to the ground state. We can also prepare specific motional states within each mode through coherent coupling, coherent control through the electronic state. So we can add and subtract phonons from our phonon mode through interactions with our electronic qubit. And so this is like the Jaynes-Cummings Hamiltonian that you see with a single particle in a cavity, except but we can both add and subtract phonons. So it's slightly richer, but it's exactly the same physics. And maybe the most important thing in terms of quantum computing is that because these modes are shared between ions, so any ion within the trap, they have these emotional modes that are shared, and they can be used to mediate entanglement. So we can entangle the electron spin with the motion, and then if we drive the motion together, that the motion depends on the electronic state, and so we can drive entanglement. And I won't go into detail exactly how we do it, but just to say that the motion allows us to create entanglement. If we have n ions trapped in a single harmonic potential, we can drive entangling gates between any arbitrary subset of those ions. How fast that might be is another question, but we can in principle. Okay, and so with those motional modes, we can do 2 qubit gates. There's some crazy protocols that can run things faster, but in general, the highest fidelity 2 qubit gates are run in around 10 to 100 microseconds. So that would take us 325 years or 32.5 years to simulate nitrogenase with, record levels, 3 nines of fidelity. And I think actually, since I put this number, maybe we can get almost 4 nines Oxford ionics, although they don't use this optical qubit, they use a ground state qubit. But, fairly low errors, even on our 2 qubit gates. But I would say one very large caveat is that these numbers have always been recorded for a 2 qubit chain. Okay, so where you only have 2 qubits together. And as you increase the number of qubits in your chain, although you get this any-to-any connectivity, which is very powerful, your gates become slower and your errors become higher. And so that's kind of one architecture question we might ask that I'll talk about nearer to the end. How many qubits do you want in each chain? All right, so this is our qubit. If we only have 1 or 2 of them, pretty high fidelity. But we need to get from this very high fidelity qubit to this very, very large system. And what I'll talk about today is the optical and electrical engineering that we do to bridge that gap, to hopefully at some point. Yeah.
Distance between your ions and your trap?
Yeah, about 5 microns, micron scale.
Is the time that you need for a controlled operation, is that limited?
For the 2 qubit gate?
Yes.
Yeah, great question. So this is limited by the motional frequency. So I said before that we have about 1 megahertz trapping frequency. That's a pretty standard trap frequency order of magnitude. But I would argue that if to build a really scaled quantum computer, we need 100 megahertz trapping frequencies so that we can increase this speed by 2 orders of magnitude. So you can run non-adiabatic gates where you're running a gate within a fraction of a motional period, but those are usually lower fidelity and require like some ridiculous amount of laser power. So these gates, adiabatic is not adiabatic in terms of what, but it's adiabatic at least in terms of the motional mode, the motion. And yeah, so this time scale is set by the motional frequency. Any questions? Now we'll go into how we can scale to millions of qubits eventually, maybe. All right, so the general architecture that we have in mind is some sort of modular architecture where we have these, each module is a group of ions trapped in a single potential. And as I've indicated here, they all can be connected through laser interactions. And you would need 1 laser per qubit individually controlled to be able to pick out which interactions you're doing at any given time. And then you would connect different modules either through optical links, which are slow, so they could be used for long distance links, or what is done more usually is physical links, which are quite fast. And what I mean by physical links is actually creating waveforms on your electrodes such that some of your ions physically move from trap to trap. Okay, so and there again, the speed of that operation is limited by the time scale of your trap frequency. So if we could make our trap frequency 2 orders of magnitude larger, then we could make these physical links 2 orders of magnitude faster. And so, yeah, there's been really incredible demonstrations done by having only 2 ions per trapping potential and shuttling them around using these physical links. So the idea is that, if we were able to have this modular architecture, then we could increase the number of qubits without increasing error rate. But by which I mean, the error rate, adding another module doesn't affect the error rate of your original module, right? So ideally you could copy and paste and get from 10 to 1 million. So the current state of the art, I'll just talk about 2 companies, although there are of course more, but the 2 trapped ion companies that are have shown the quantum computation with the largest number of ions. One is Quantinuum, and there they use this shuttling to kind of its fullest extent. So they only have 2 ions per module, and they've shown up to, I think now 50 ions. In this paper, they had, I think, about 32. So they only have 2 ions at any given trap, and they have 4 interaction zones. So they have 4 places where they can shine lasers. And in those places, they could have a single qubit and run single qubit gates, or they could have 2 qubits and run 2 qubit gates. And they can kind of move these around and flip them around however they want to get arbitrary conductivity between these 30 qubits. The downside here is that the shuttling takes a lot of time and you have to cool afterwards. So even if they can run really fast gates or fairly fast gates, state-of-the-art fast gates at the very least, they have to cool. And so depending on what they're doing, more than 50% of their time is spent shuttling and cooling, which is not great if you think about scaling by orders of magnitude. The other company is IonQ, and they're taking a different approach. They have tens of ions all trapped together in a single potential. And here, interestingly, both these architectures get similar fidelities and run at similar speeds. So even if here they don't have to do shuttling, because they're in this long ion chain, their gates take longer and are slightly lower fidelity. So it all comes out in the wash currently. And in both cases, they're limited to tens of qubits. Okay, so let's start looking at the figures of merit that we need to be able to get to these million of qubit number. So the first thing is kind of to Vahid's question is, what is the best architecture that we want to use for our trap? What we want is a low heating rate. This heating rate means that when an ion is susceptible to all electric field noise will slowly increase the phonon occupation in a thermal manner, which is why we call it a heating rate. And there's a lot of noise that comes from the surface. And so if our ion is closer to surfaces, we'll have a higher heating rate. It's also kind of scales with frequency. So if we have a higher trap frequency, we'll have a lower heating rate. So we want our ions to be far away from surfaces, but we want high trap frequency. We also would like a very harmonic trap. So, this kind of all relies on the fact that we have this very harmonic oscillator. Any anharmonicities, they could be interesting because what they can cause is parametric coupling between different motional modes. But for an ideal quantum computer, we probably want to avoid that. And so any anharmonicity is just kind of reducing the conversion of our voltage to trap frequency. So we want a very harmonic trap. All of this is going to come together, and we want this very high 2 orders of magnitude higher trap frequency so we can get our fast gates and our fast shuttling and low heating rates. And then finally, we want to be sure that we can actually make this in some sort of reproducible manner, and at least there's some sort of path to fabrication in a foundry process. Okay, and so we looked at 3 different general geometries. Let's see if I can move this out of the way. Okay, 3 different general geometries. The first is the surface trap. So that's what most traps are used. This is this unfolded trap. We then looked at a middle ground where we have our surface trap, but we just have a ground plane on top. So instead of having our ground plane up at infinity, we bring it closer, and we're going to see that that does help things a little bit. And then what will be the hardest to fabricate, but the best in the end, is a trap that looks a lot like that original Paul trap where we have 4 blades. But now we will segment some for DC control, and this would be made on 2 wafers kind of bonded together. But this requires precision alignment. Okay. And we can already see that as we increase the complexity of the trap or make it more 3D, things get better. So this is kind of three comparable geometries for the 3 different options. And you can see a few things. The first, you can kind of just qualitatively see that the trapping region gets larger with each, or the trap depth gets larger with each, and also that the trap depth gets larger in each. So here we have about 1 millivolt, and here we have 80 millielectron volts, and this can actually be made higher if this is optimized a little bit more. So we get kind of 2 orders of magnitude improvement by going from the surface trap to the cross RF trap. And these are all made with the same exact voltage. So we can get, trap depths that are much larger. Even with the surface trap, we can get trap depths that are much larger than room temperature, which is nice for keeping our ions trapped for a long time. Okay. We can look also at the trap frequency. And this is for the surface trap. So that's this red dotted line. On the x-axis, we have the height. So this is either the height from the ground plane to the electrodes or the height between these 2 wafers. So we're sweeping that, and we see how the trap frequency changes for a set amount of voltage. And we see that we can get much higher trap frequency for both geometries than we can for the surface trap. And if we put together so this is while keeping the drive frequency the same. But if we put together this fact And the fact that the cross RF trap gives a much more harmonic potential. We can actually get 100 times higher trap frequency in the cross RF geometry than we can in the surface trap with the same voltage. So this gives us hope. It's a little bit trickier than that. It's not that I can just, go to my friendly fab buddies and tell us to make it and we can get 100 megahertz tomorrow. But we can hope to get 100 megahertz with reasonable voltages if we're able to create a geometry that looks like this. No, H is, in this case, it's about 100 microns. So and this limit is because it's limited by the separation. So if our ion was to be 10 microns from the surface, we'd really see a lot of electric field noise. So electric field noise due to surfaces tends to scale as d to the 4. So you really win a lot by going higher. So your normal ion trap distance is on the order of 100 microns.
Conductivity doesn't help.
So there has been one study where people tried to do superconducting traps. This was out of Lincoln Labs, and it did not help. But I will say also that there's been tons of research about where this electric field noise might come from. It's orders of magnitude higher than you'd expect from Johnson noise. So it's coming from some disorder in the surface.
It's kind of a patch field that one talks about.
That's the idea, that there are these patch potentials that are, fluctuating due to, there are many different theories that cause that, but the size of the patches, there's also, basically, there have been a lot of measurements and none of them agree. Some people measure distance scaling, they measure d to the 4th. That's what most people measure. Some people measure lower than that, and some people measure higher exponents than that. I would say also that this is, so for instance, that superconducting measurement, one thing that's really difficult there is that you also get electric field noise from the environment. And so to make sure that your qubit is limited by electric field noise from your surface is very tricky. So we have some ideas about how to do this by measuring spatial correlations between two traps, because your electric field noise from the surface should be uncorrelated, but your electric field noise from the surrounding should be correlated, and hoping to get a more quantitative understanding of what's coming from the surface. But so far, there's been tons of studies and no one knows. It's very unclear. But things get better at cryo. So some, the companies just say, okay, let's go to cryo. There's no reason to be at cryo for a trapped ion system. We can run all at room temperature, but going to cryo allows you to fix the electric field noise. If you have money, you can fix electric field noise. You can also fix your vacuum problems. Yeah. So now, kind of armed with that knowledge, what we're trying to do now is fabricate these sorts of traps, and also kind of figure out exactly how high a trap frequency we can get. In a manner that's scalable. And so what I mean by that is something that takes only about 10 volts. It doesn't help if we need hundreds of volts, especially because at some point we're going to need a centimeter scale chip. We're going to get a lot of RF losses. So we want to run with as low as power as possible, so we get as low power dissipation as possible. Okay, so let's say now we're using this 3D geometry. We can trap millions of qubits. Now, how do we measure and control them? So I'll talk about measuring, but a lot of what I'll talk about could be immediately applied to control as well, with some changes. So if you remember from the trapped ion level scheme, we need a lot of different wavelengths, and spanning from around 400 nanometers up to the near IR around 850 nanometers. And for each of these wavelengths, we kind of need one controllable beam per ion. So we need some sort of source that can create enough power with the frequency stability that we need. we need to be able to modulate the amplitude, frequency, and phase of each of those beams at that microsecond scale. And then we also need to be able to route and focus the light. So we have some work mostly in collaboration with my PhD group with Dirk Englund, who makes these active integrated circuits, about how to build modulators that can give us the control that we need to run these qubits. And this is an active field within itself, and we wrote this review paper. So if anyone wants to learn more about active components in the visible, you can read about it here. But today I want to focus on the routing and focusing part of the equation. So let's say we can make the light, let's say that we can modulate the light. How do we get that light to the ions? And as I've said before, the ions are very particular, so we want to keep them very far away from any dielectrics or weird materials. And so we're going to need some sort of free space control over the spatial extent of the beams. And the specifications that we need are larger than 40 dB ion isolation if we want to control individual ions at a time, more or less at least. We need to have this multi-wavelength operation. And what I'm going to talk about now is how to get the centimeter scale field of view. So how people currently read out ions is that they have, these are maybe like single ions in different trapping potentials, or maybe they're chains of ions in different trapping potentials. But what people do now is that they use a very high numerical aperture objective. Remember, we have to be pretty far away from our ion. So getting a high NA objective is not trivial. And this high NA objective kind of has a low field of view. And there's, some inherent trade-off between the numerical aperture and the field of view if you want to keep your optic not like ridiculously large. And if we think about what we'll need for a megaqubit system, kind of looking at current trap sizes, we would need centimeter scale, a centimeter, almost like a wafer scale, 5 centimeters system. And so there's kind of two options if we want to read out and control all of the ions along these 5 centimeters. One option is to spend a lot of money and build a really, really huge objective like they have for fab. And this is not impossible, right? The fabs that make these nanometer, I'm blanking. I want to say Intel, but that's not the best. TSMC, thank you. Yeah. TSMC, for instance, has these huge 400, huge lenses. So it's not out of reason that we could spend a lot of money and just make a really, really huge objective that would also have to work at many wavelengths and have, micron scale resolution over a wafer scale. So it's not out of the question. And that's definitely one possibility. But the possibility that we are going to take instead is monolithically integrate lenses at every single ion position. Okay. And so the idea would be that you come in with some now collimated light, or either way you want. Either you come in with some mostly collimated light and then you focus it directly at the ion with some integrated lens, or you can think about, and what I'm going to talk about is the opposite, where the ion fluoresces and then you collect some of that light. But now that light is collected into a collimated beam, which means that you can just use a very simple lens or even just a detector here. Okay. And so you don't need now this huge, super expensive objective. But you need to spend a lot of, you need to create this system. Okay. And, as I said before, our ion, we like to keep it very far away from any dielectrics. So it'd be nice if we can, put our lens right next to it, but we want to keep it hundreds of microns away. And we also need this high collection efficiency. So we play one little trick, which is that we undercut our wafer so that we have these, we can keep our dielectric super far from our ion and also shielded from our ion while still kind of getting the benefit of having a dielectric. And so what we do is we do a 2-step fab process where we fab big undercuts and then we flip the thing over and fab the places over which our ion will be trapped. This whole thing is bonded to an oxide wafer. And then we pattern metal lenses on the bottom of this oxide layer. I guess I have it drawn all in oxide, which is bad on my part. These are actually in a thin silicon nitride layer. Okay, and we use metal lenses because this is full monolithic integration. We can get really good alignment between the metal lens and our ion. And for this particular project, we don't really use the full power of metal lenses, but you could also imagine designing a more exciting metal lens that allows you polarization control or allows you multiple wavelength control. But in this project, we're really just this metal lens. All it does is it focuses all of the light that gets collected into this aperture, or sorry, collimates the light that gets collected into the aperture. Okay, and here are some pictures. So here are the undercuts. These are the electrodes up here. And we have this one big undercut. So this is all silicon with the boron silicon glass on the bottom here. And with this image here, you can see, so this is the middle ground electrode, and these are two RF electrodes. This is the space between the electrodes, and this is the slit over which the ion will be trapped. And these concentric circles, this is an overlaid image. These concentric circles are the metal lens that is fabricated on the bottom of this trap. Okay.
Is the Fresnel lens, or is that are these kind of nano grading of the index to get something, or how's that?
Yeah, so this particular one, in the end, it ends up being like, you can see that it looks very Fresnel lensy, but it's not a Fresnel lens. It's really these pillars. So where they have these scatterers, and the diameter of the scatterer, determines how much light is scattered at that particular location. And with the whole, they're placed sub-wavelengths. They're sub-wavelength scatterers. And if you look at the effect across the whole beam, then you get this collimating effect. Yeah. And the metal lens expert in the room, is Arkham Majumdar and Johannes Freuk, who are also at UW. This metal lens, we more or less designed ourselves because it's fairly simple, but they can really play a lot of magic with these metal lenses. And they're working on a design now that can take multiple wavelengths of light and give either take multiple wavelengths of light and focus them all to the same location, but also take one beam of light and split it so that we can control multiple traps at once. If you're an expert, I think talking with them, they make it sound like you can make these metal lenses do anything. It's not exactly true, but you can make them do a lot. And we're like pushing the limits because, again, we need much, more precise beam control than a lot of applications.
But I mean, these designs are strongly chromatic, right? And you, I guess, have the advantage that you have very specific, narrow.
That's right. Yeah. So we can get multi-wavelength operation, but it's really like it's not broadband operation. It's operation at 390, and it's better because actually our three wavelengths that for the other project is 397, 866, and 854. So they're very separated, and the 866 and 854 are close enough that it's okay. But yeah, it's not unlimited what you can do. Okay, so this is an image of the beam when we send in collimated light to the metal lens and measure what the beam looks like at the focus. We see this fairly nice spot at about 2 microns. So this might have issues if we wanted to, we'll talk about optical crosstalk if we wanted to use this for control at 729 nanometers. But for collection, this is totally fine. And we expect to get about 90% of the light that makes it through the slit should be focused well by the metal lens. So what we really want to show with this device is that we can even we can collect over many locations at once. And indeed, that's what we see when we do the measurement. So what we're doing here is we have an artificial ion. So we create an ion by focusing a beam of light to 1 micron. So it has a higher numerical aperture than our slit. So we make sure that our slit is the limiting effect in this system. And then we see what happens when we collect it through a 20x objective with 0.6 NA. You can see, so it's all normalized to what we collect through there. We can see that we get very high collection efficiency, but we can really only collect over 1 millimeter, right? And so that's kind of what's shown here, right? We wouldn't be able to collect any light from this neighboring traps. We need to make this objective, much larger if we wanted to be able to collect efficiently from these neighboring traps. On the other hand, our meta lens did not work quite as well as we expected. We expected to get at least 90% up here, but we only got 55% or so. But still, we see that the collection efficiency basically remains unchanged as we collect from different traps, or as we move kind of our system with respect to our detector. And this would just basically go on forever as long as our detector is big enough. Okay, so and they're fabricating a second sample now with some of the things that we learned from the first sample to hopefully bump that up higher. Okay. And the dream in the end is to have some system like this where you have some detection layer that gets directly imaged onto maybe detectors that are integrated with some classical logic so that you can do all the decoding that you need for error correction all right here, that would then get fed back to your laser control, all integrated with this 3D architecture that I presented before. Okay. And as I said, we're now working also to expand our wavelength control as well. All right. Any questions about this? So in the last 15 minutes or so, I want to look ahead to 2 types of errors that will become more prominent as we scale our system. So as I said, there are these 2 different architectures. In Quantinuum, they have 2 ions per chain. In IonQ, they have 30. And when you add, one question that one could ask, and one question that guides a lot of our work, is how many ions is the optimal number of ions per module? And there's probably some answer to that question that is given by the algorithm that you want to encode or the error correcting code that you want to use. So maybe if you want to use a 7-qubit Steen code, you should have 7 qubits per module as a simple example. But we're looking at it from a error perspective and a kind of optical infrastructure perspective. So as you add ions, you get this higher connectivity without shuttling. You maybe reduce the number of gates that you do if you count like the swapping as a gate and the shuttling as gates. You get lower error correction thresholds because you have this direct all-to-all connectivity. And so there's, and you reduce your cooling and shuttling time. But you lose in entanglement fidelity, partially due to optical crosstalk errors, which I'll talk about now. These are coherent errors that actually we can correct for. Also, parallel gates are really difficult, which is a problem for error correction. Although you can still get parallel gates, still between 2 different trapping sites. So it's not a killer for error correction, but it makes things harder. And then you can also have correlated errors due to local fields. And I'll talk about now background gas collections, and correlated errors are also a killer for error correction. Yeah, error correction relies on the fact that you can do parallel gates and you have no correlated errors. All right, so let's talk first about optical crosstalk. So if I have a 5-ion chain, and this is for 1 megahertz axial trap frequency, the ion-ion spacing in this case is about 4 microns. If I have a beam waist of 2.2 microns, which is like doable but non-trivial, then and for the 5-ion chain, I don't have much optical crosstalk. Which by optical crosstalk, I mean to excite these 2 ions, and I don't excite these 3 ions at all. Okay, and we'll quantify this in a second. But as I increase the number of ions in my chain, if I keep my trap frequency the same, they get squished closer and closer together. And you can see that like here, you basically have 100% crosstalk. Okay. So especially if we want to add more ions, but also once we integrate our optics, our beam profiles are going to be nasty. Even if we make the best lenses in the world, meta lenses in the world, they're just not going to be as good as really high quality bulk optics. So these two things mean we'll probably have more optical crosstalk. And then there's also some reason to not want to make your beam super small, even if you could, because that means that your pointing has to be more precise. And you also get polarization errors when you start to focus too tightly. Okay, so making smaller is not always better. And so this means at some point, especially if we want to kind of remain at this 10 to the minus 4 error or get even better than that to reduce our error correction thresholds, that we will have to deal with optical crosstalk. Okay, and so I'll just say that Quantinuum with their 2 ions, they've kind of like gotten rid of this problem by saying there is no such thing as crosstalk. We only ever have 2 ions, right? But maybe that's not the best long-term solution. So we started to look into what does this optical crosstalk actually do to our entangling gates, and can we fix it? And we hope that we can fix it because this is a coherent error again, right? This is some error that we can calibrate and hopefully correct for, unlike error just due to noisy control fields. Okay, so but to explain it, I need to explain a little bit more the motional mode structure of ions. So these are our 5 modes of a 5-ion chain. You can see, and each mode is characterized by 2 things. One is the mode frequency. So this is the secular frequency of the ions, the frequency of the motion in the trap. And the second is this mode coupling vector. And this mode coupling vector is how well each of the ions, or how strongly each of the ions is coupled to the motion in each mode. So in this case, we call this the common mode. All of the ions, the mode coupling vector would just be all ones, right? All of the ions are coupled in the same phase and at the same amplitude. Here, the outside ones would have opposite phase and large amplitude, and this one in the center would have 0 amplitude. Okay, and et cetera, et cetera. And this is given by solving the harmonic motion for a trap. So this is kind of set by the trap. Just the fact that you have a harmonic trap, you can calculate what your modes will be. Okay, and if we look at the entangling gate here, so this is the phase, the joint phase between our 2 ions. It's reliant. We can talk, if you'd like, we can talk more in detail about the gate, but let's just say the joint phase that you get between your ions is related to 2 things. It's related to the optical power, so the Rabi frequency on each ion. So that's omega 1 and omega 2. And it's proportional to the mode coupling for each of the 2 ions, to the mode that you're using to create this entanglement. So eta 1 and eta 2. So your Rabi frequencies are defined by your optical setup. They are, set, and there might be some extra unwanted gate between your neighbor ions due to optical crosstalk. But this mode coupling, you can pick which mode to use, and so you can pick which of these modes that you want to use for a particular entangling gate. And this is going to be the trick that we play. Okay, so one example, so I've picked this example here. We want to pick some mode where the mode coupling for our 2 target ions is much larger than the mode coupling for our neighbor ions. So for instance, in this case, we're using this lowest frequency radial mode, which for technical reasons is the mode that people usually use to entangle ions. It's due to electric field noise. You can see that the motion of all these ions is uncorrelated. So one hopes that it doesn't get heated very quickly because you expect noise from the surface to be correlated between the ions in a trap. So people often use this mode, but the best you can do, I don't think I have it here, but this is with 6% crosstalk on your middle ion, on your neighbor ions. The best you can do is 96% fidelity. But if I pick a different mode, then I can get 2 nines of fidelity, right? And so this is a pretty simple concept, but it can be applied without any computational effort and without any extra effort, experimental effort. And if you go through all of the different mode pairs for all of your ions, so this is ion 1, ion 2, the fidelity of the entanglement gate between ion 1 and ion 2 when using mode 0, 1, 2, 3 in the common mode. And lighter is better in this case. So we can always pick the best mode to use and run our gate off that one mode. And we have implemented that on a system at Sandia with 5 ions and shown this to be true. And I'd say for the experts in the room, these are all slow gates. So this is all in the order of 200 microseconds, but you can run fast gates as well. And it turns out that you can make pulse sequences that you can use your favorite fast gate, and you can always make that fast gate insensitive to optical crosstalk. And I can talk more about that later if you're interested. So basically what we've learned here is that even if optical crosstalk will get worse, we can correct for optical crosstalk in a system. Okay, and then maybe just really briefly, I'll talk about background gas collisions. So we have very high vacuum, 10 to the minus 11 torr or so, kind of limited by our vacuum gauges, or that measurement's limited by our vacuum gauges at the moment. But we still have some hydrogen molecules that are coming out of our stainless steel. And every once in a while, those hydrogen molecules interact with an ion. And if we're very unlucky, and if it comes close, it can cause a Langevin collision and send all of that energy into the ion and cause the crystal to become decrystallized, or even the ion to be ejected from the trap. And so currently these errors, this error is, this is the error that you'd expect. This is the error that you get, this is the error that you accept. So you expect a collision per minute for a 10 ion chain, which is kind of like annoying right now when you're running an experiment. And actually these rates are even higher for experiments by a couple orders of magnitude. So you get like a few, maybe 10 to 100 collisions per minute. But again, that's fine. Like if you're running an experiment, the experiment only takes like 100 milliseconds. If you happen to get in a collision and you notice an ion is gone, you just throw out that run and run it again, right? But when we get to millions of ions, this will actually be a pretty appreciable error. So we'd like to understand this sooner rather than later. And there's 3 types of errors that you can get through collisions. The first is that you can get motional heating. This reduces the fidelity of entangling gates. You can get reordering errors, and you can get ion loss. And both of these are correlated errors, which again are bad for error correction. And so and also, so there's basically no data on these collisions, mostly because, as I said, it's just kind of annoyance now, not a big error source. But the data that do exist don't show the expected scaling. So this on the x-axis, we have the number of ions in the chain. This is all taken from the literature, which got removed. Sorry, this is taken from the literature, mostly from Innsbruck. These are 2 different papers, both from Innsbruck. And on the y-axis, we have the reorder error per ion. So you'd expect that the reorder error per ion would stay constant. But you actually see this downward trend, which is pretty weird. And also there are many orders of magnitude higher than the rate that you would expect from like a simple understanding of the collisional cross-section. Okay, so, but to understand this and then to be able to fix it, we need both more data and a better model. So we are planning to take data in our chamber by varying all the different parameters that we can vary and seeing how the collision rate changes. And we have also created code to actually simulate the dynamics between the hydrogen molecules and the calcium ions. And we have a full dynamic trapping potential, as well as we can see how cooling affects. And this is a simulation run on our GPU where we have we have a 10 ion chain, and we're changing where we're sending in our hydrogen atom, like how close we are sending a hydrogen atom into one of our ions. And this is the speed of that atom. And the color tells us what the percentage of what probability we have for the ion change to reorder or for us to lose an ion. So you can see for lower frequencies, we have a much larger cross-section. Lower velocities, we have a much larger cross-section. But for higher velocities, we still have a very high probability to reorder. And for those, this is the average. 1 millimeter per second is about the average speed of a hydrogen molecule at room temperature. Okay. But our hope is to get some nice agreement between our experiment and our simulations so that we can then design traps even further to reduce the reorder probability. Okay. And now just to finish, these are the 4 things that I talked about. And then if anybody wants to ask me other questions, this is a system that I'm really excited about. It's going to be a quick change chamber. So hopefully we can get to UHV in about a few hours instead of a few weeks, and change out lots of different samples and still be able to run ion measurements on those samples. And we also have work about how to quickly control motional modes using optical tweezers. We got tired of our neutral atom friends always talking about optical tweezers, so we wanted to play with them too. As I said, we have work on quantum sensing, and then some more work with our computer science colleagues about how to actually figure out what the best architecture is by considering the physics and not just their idealized qubit model. And with that, I'll stop and happy to take any more questions.
Thank you very much for the nice talk. Are there any questions from the audience? Yeah, Masha is first.
Thank you for the talk. So did you test your collection control mechanism design on some simpler emitters, like for instance NV centers you can integrate into easily, you can easily scale up the number, right?
Yeah. The quick answer is no. So what we tested it on was our fake ion. So we created this 1 micron spot. And then as soon as this chamber is up and running, we can test it on real ions. But we have not tested it on NV centers.
Other people who work, is this?
So meta lenses are definitely not new, although it's like a field that is still, that's current. So maybe the most related work is people who use meta lenses to create 2D mots. So you can have one beam coming in and then it creates the, I'm not a mod expert, the 6 lasers, I think. I think you have meta lens on top and bottom and you create, breaks into 3 and then it retroflects. So that's probably the most similar use of meta lenses, but as far as I know, no one's done it for collection.
It's just a non-expert curiosity. So what is the reason for choosing calcium platform? And is this, what's the figure of merit? And is this the best platform for scalability?
So I would say the tongue-in-cheek answer is the reason is kind of historical. It's the qubit that I worked with during my postdoc. And so I know all of its, issues and I know, but maybe the more scientific answer is that all of the wavelengths are pretty nice. Our lowest wavelength for qubit control is 397 nanometers. For the other kind of general type of qubits could be a qubit in the ground state where you have to use a Raman transition and there you need a lot of power. Sorry, that was louder than expected. And since some of our work is focused on integration, getting that kind of, for Raman beams, you need tens to hundreds of milliwatts per ion, and that really just doesn't work well with an integrated photonics platform. So for me, for the problems I want to solve, this qubit seemed best. I think a lot of the problems, if we solve some problems, they can be immediately that technology can immediately be transferred to other qubit types as well.
As far as I got the existing, let's say, networks by continuum and so on, they have a kind of constant number of qubits in the different modules, so kind of simple geometry somehow. Would you say that somehow, or where the field is going, that in principle there are optimal solutions that even algorithmic dependent, you have kind of optimized structure with different modules, or is it just from the engineering side that you would like to have identical modules?
I think that this is a very interesting question, and the field is definitely not settled. There are some people working on compilation that really kind of could have a more complicated architecture, as you suggest, depending on the algorithm. But so far, the experimental implementations have just focused on like a simple architecture. But I think in the future, there will definitely be algorithmic dependent qubit layouts.
Thanks. Very interesting talk. For the ionic quantum sensing, what is now a practical, useful, real-world application that I can explain with parents?
Yeah. Yeah. So I don't know if your parents would like this explanation, but I'll say it to you and then you can say it. So I think that the best use for a trapped ion quantum sensor, and this is going to sound a little bit like a cop-out, but is to calibrate to calibrate a quantum computer. You don't like that answer.
Yeah.
So the reason that I say that is because, so I'm like I think just in general, okay, maybe a lot of quantum sensors that exist are not super quantum. You have like a huge ensemble of 2-level systems that can sense some fields. But the reason for that is the root n scaling you get from just having billions of atoms that are not super coherent is always going to win out from a single or like 10 super good qubits. The only small deviation from that is the work that we did on intermittent signal sensing. And so there, if you have a stochastic signal, so the mean is 0, but there is some variance and you want to detect that variance, there actually it helps to have a very high fidelity sensor, because what you're doing is you're measuring deviations from the eigenstate. So in that very particular case, it does help to have high fidelity, but just in general, you're better off having a billion kind of crappy atoms than having one perfect ion. So that's why I would say it feels like a cop-out, but I think it is like a powerful thing. I do think that like there will have to be quantum sensing to it is a quantum sensing problem, the phase estimation to calibrate a full-scale quantum computer. And the best thing to do that, of course, is going to be your qubits. So I think that's the way to frame the quantum sensing problem. But your parents might not like it.
Any more questions? Maybe I have one. When you had this picture of a 5 by 5 centimeter square array, it wasn't quite clear to me what exactly was the architecture. Do you still involve some shuttling or?
Yeah, that would be like if you had a Manhattan grid that you were shuttling on. So that would be, and so the way I got to that 5 by 5 centimeter is that if you have about 500 microns between traps and you have in the end 10 ions per each trap, that's how we get that number. But yeah, it's a Manhattan grid of different traps, with assuming that you could shuttle between them in any way that you want.
Just one last thing. Maybe you would expect then your collision problems to also be solved if you went to a cryostat, right?
Yeah, so that's right. Collision rates are lower at cryostat because your pressure, you get cryo pumping. I would say 2 things in relation to that. First of all, at your lower average velocity, each collision that you have is more painful because more energy is switched between your hydrogen and your calcium, because the interaction time is longer because it's moving on average slower. So that's one thing. The second thing is again, it's this expensive fix for a problem that maybe there's a different solution for. And then I had a third thing, which I forget. Oh, and the third thing is that still your local pressure might be higher than you think because you get local outgassing from your trap. So
I guess I'm thinking that a very cold stainless surface is not going to bubble hydrogen as much. But
that's true. Your closest surface though is some like gold that you I mean, in current systems, it's some gold that you kind of like kind of sputtered not very well on your system. It's your electrode surface. But your point is taken. Like, and that's what they do. They just get cold. And that solves a lot of their problems. But maybe I would argue that we could be smarter.
just as an anecdote, you're where the ion trap Nobel Prize was given. You're actually in those rooms. In the room of Damon.
Oh, sorry. You mean at Seattle?
Yeah.
Yeah. That's right. Yeah, it's a very. Sorry, I thought you meant here. I was
no,
surprised.
that's still to come. We're hiring them.
Yes, it's a very storied history, and there's a quadrupole trap engraved on the physics building.
Okay, with that, we thank Sara again for the nice talk.